Great to have you. Lucy is from Exponent. And so this morning we heard from innovations in the material side and about the market landscape. And then we're going to now hear about a very important point, which is safety. So the stage is yours, and you have something about 20 minutes. And
All right, can you see the
we can
presentation already?
see your presentation. We can hear you, and we can see you very well. So good luck.
All right, perfect, thank you. Thanks for the introduction. So today I would like to talk about the safety of solid-state batteries. But before we dive into the subject, a little bit about myself. So I am Lucy Buannic, a senior scientist at Exponent, and I am based in the Boston office in the USA. I have about 7 years working in solid-state batteries, both at the material level and then taking these materials into prototypes on pilot line as part of the industry. As after joining Exponent, I've gained expertise in failure analysis as well as thermal runaway characterization and battery quality assessment. In terms of my background, I received my PhD at Stony Brook University with Professor Claire Gray studying ceramic electrolytes for solid oxide fuel cells. And these materials are typically proton and oxygen conductors. Exponent is a scientific consulting firm, and we gather close to 1,000 full-time consultants, all of them having a PhDs, and we can answer questions on any scientific problem. We have offices scattered throughout the US, and we also have a presence in Europe and in Asia. And this comes very handy when it comes to battery-related work. On the business side of things, we support corporations and law firms with their legal issues, so we can help them sort out IP questions, anything related to science once again. And we also have a good amount of projects that are more proactive, where companies would like to assess the risk associated with a new product or understand why some of them are failing prior making a huge recall. All right, so let's dive into the today's topic. So traditional lithium-ion batteries contain a solvent-based liquid electrolyte, which is flammable and toxic. And in solid-state batteries, this liquid electrolyte is replaced by a solid-state material, and we have the main three families that these materials can be chosen from, each one's having their advantages and drawbacks. And what really we're trying to achieve with the solid-state batteries is not only improve the safety of rechargeable batteries by removal of the flammable electrolyte, but also increase the amount of energy that is packed into the cell. And that can only be achieved by incorporating lithium metal at the anode and a high voltage cathode material. Now, lithium-ion batteries are governed by a large variety of standards, and the purpose of this standard is really to try to understand and predict how the batteries are going to fail when they are released to the market, and understand how that can impact the end user. The other aspect of these standards is that when there is a change in the chemistry or in the design of a cell, or as we go through various generations of cells, we can use these standards and prior results to compare old and new technologies and evaluate those changes in design. Now, this is the reason why a lot of OEMs are using these designs to start evaluating solid-state battery technologies. But as we've learned from past experience, these standards are not always enough to catch or predict all hazards and risks associated with releasing a new battery in the market. We've observed that in the past with the Galaxy Note 7 and the 787 Dreamliner batteries, which have led to huge recalls and a lot of budget